to build an interactive environment, the quickest way to understand the underlying mechanics is to create this exact result. You don't need dedicated software to do it. Every modern web browser has a rendering engine built in, and you can write the instructions for it using any standard text editor. Step 1 is setting up the visual rules. Step 2 is defining the animation logic, specifically how speed variables interact with screen boundaries. Step 3 is capturing user input to trigger the process. We are going to build this line by line. If you have never written a script before, the logic is straightforward enough to follow from a blank page to the final product. Creating complex visual motion on a screen comes down to combining basic arithmetic with the tools your browser already provides. We start by building our environment. To make the colors pop, we set the document's body to a very dark blue, hex code 050816, creating a high contrast background. Next, we design our target object. We give it a strict set of physical dimensions, exactly 70 pixels wide and 70 pixels tall. To give this flat square a sense of physical volume, we apply a linear CSS gradient. By angling the gradient at 135 degrees and fading from cyan to white, the browser renders a simulated shadow, creating a three-dimensional illusion. We finish the look by applying a box shadow property. Adding a 25-pixel cyan blur around the outer edge projects a neon glow against our dark background. By locking these aesthetic rules inside a single CSS class, we isolate the visual presentation. When we write our script, we can treat this object as a simple mathematical block. Before we can spawn a single cube, the browser needs a way to remember it exists. Without a tracking system, objects will render, but we won't be able to move them. We solve this by defining an array. Think of this as a master inventory list that will log the exact status of every active cube on the screen. To create a cube, our script generates a standard HTML division element, tags it with the CSS class we built earlier, and appends it to the document body. This diagram shows the grid logic the browser uses. The exact moment the browser generates the square, we push its starting horizontal X and vertical Y coordinates directly into our array. The visible cube represents the specific values stored in our array. The browser renders the object as a consequence of registering its coordinates in the data record. To make the object move, we use an animation loop. This mechanism fires every single frame, recalculating the array data and updating the screen to match. This diagram breaks down velocity. We assign a speed value of 3 to the x-axis and 2 to the y-axis. By combining horizontal and vertical speeds every frame, the result is smooth, diagonal motion. If the cube travels infinitely, it leaves the viewable screen. To keep it contained, we write a boundary check. When the object's x-coordinate hits the right edge of the window, we multiply its velocity by -1 to reverse its direction. But the math has a flaw. Because the browser measures the object from its absolute top left origin point, the entire 70-pixel width of the box slides off-screen before the calculation triggers the reversal. To fix this, we subtract 70 pixels from the total window width in our collision logic. We offset the boundary by the exact physical width of the object. The math now accounts for the physical shape of the box, creating a perfect surface collision. With a stable physics loop, we shift from automatic generation to placing the objects manually. We attach an event listener to the entire document. This acts as a passive monitor, waiting for a specific user action, like a mouse click. This diagram illustrates what the listener captures. When you click, the event records the precise screen coordinates of your cursor and passes them to our creation function. If we apply those raw numbers directly, the browser anchors the top left corner of the box exactly where the mouse clicked, leaving the object hanging awkwardly down and to the right. We apply another offset. Subtracting exactly 35 pixels from both the X and Y coordinates shifts the entire 70-pixel box up and left, centering it perfectly beneath the user's cursor. A mouse click works on a desktop, but a mobile device doesn't have a cursor. If we try to run this on a phone, the input fails. We need a second listener designed specifically to detect touch starts. Because a user might use multiple fingers at once, touch events generate an array of data. We write a simple condition. If it's a touch event, look specifically at the first index, grab those coordinates, and ignore the rest. Translating the raw input into standard numbers means that the identical underlying math now handles both clicks and taps flawlessly. Tap your screen repeatedly, and the logic scales up instantly. Hundreds of objects generate at exact touchpoints, populate the inventory array, and run through the physics loop without breaking the boundary limits. This in simple parameters we established. You have the script. Now you can alter it. Go to the variables and double the velocity numbers to speed up the loop. Change the CSS dimensions to 10 pixels to simulate falling sand, or swap the cyan gradient for red. Mastering these foundational logic blocks gives you total control over the environment. Open your text editor.